2015 Big Bear.
April.
April?
April. Close enough.
That's April, that's right.
April and it's the 20.
Next month is May, that's right. This is the April 2015 Big Bear Valley Astronomical Society's virtual lecture. Before we get started, I'd like to say how gratified I've been that with the quality of the lectures we've been attracting to this forum. You may recall last month John Varsic, before that Dale Gary. We've had Don Jennings, who spoke on Cassini observations of Saturn's moons. Tom Ayers speaking on Hubble telescope science. I'm sure I'll remember Matt Penn speaking. Well, this evening is certainly no exception to that. We have Dr. Pedro Sada. Pedro received his PhD from New Mexico State in 1993, I think it was. Pedro is now a professor at, excuse me for not trying to pronounce it in Spanish, the University of Monterrey in Mexico. Pedro is a frequent observer at Kitt Peak, such telescopes as the 2.1 meter McMath Pierce, and I know he's had several observing runs on, I believe is the infrared telescope facility, IRTF, in Mauna Kea, Hawaii. When he's not observing on those telescopes, he takes data and very good science on a much more modest telescope, a commercial 14-inch Meade, like off the shelf, like any of us could get. And this is a talk I've been hoping to get him to give for quite a while. Pedro does exoplanet photometry using this very modest equipment because, well, that's what he has access to when he doesn't have an observing run on a major observatory. So this evening he's going to describe exoplanet transit photometry with a small commercial telescope. So please welcome Dr. Pedro Sada.
Okay, can you hear me okay?
Yes.
Yes. Yep.
Yes.
Can you hear me?
Yes.
Yes, sorry.
Okay, just checking. Well, thank you very much for the invitation. This is a topic that is kind of close to me in the sense, like Claude was saying. I like to play with big telescopes, but here in Mexico we have not many resources, so I figured out how to maximize the resources that we have. So I came up with this idea after a student of mine said, hey, let's look at some transits of extrasolar planets long time ago, when there were only like 2 transiting exoplanets known. And at first I dismissed it, but then I thought about it seriously, and well, this is sort of the state of what's going on with this project so far. So I call it characterization of extrasolar planets using the light curves obtained at the University of Monterrey Observatory. So if we could get the first slide, please. That is the observatory that I have. As you can see, it's not very big. I set it up in 1998. I do have the Minor Planet Center code number 720 for observations of asteroids. The main telescope is a 14-inch Meade LX200, which I just upgraded to an LX600, still 14-inch. Basically, it gives me a slightly bigger field of view, and it's better optics, and it's basically like 10 years newer or something. I do have a secondary pier on the left that usually has an 8-inch telescope or sometimes a 7-inch telescope, also commercial made.
Pedro, do you mind questions along the way here?
No, if you can interrupt me anytime.
Okay, if the hand goes up, I'll turn the camera around.
Okay. The dome is a 2-meter dome, basically, and the only thing that fits inside is the telescope. So there's a pier like the one on the left inside the dome. I have a regular CCD camera, Santa Barbara STL 1301E, I think, with photometric filters, the weather station, you can see over there the wind measuring over there on the right. And it's remotely operated and automatic, and there's a big asterisk there because I operate it from right behind there, there's a room, so. It's just a few meters, but still it's better than being inside the dome, which is rather small. So that's basically the observatory that we have. Next slide. And these are the projects we do with that observatory. We started with asteroid, we started with asteroid occultations and lunar occultations, the second and the third. We've also done asteroid astrometry, asteroid photometry, variable star photometry, and then the last project was photometry of transits of extrasolar planets. So we have basically guided the observatory to doing simple stuff. Astrometry and photometry of whatever we can get our hands on. No deep sky objects. We are suburban. We live in the city, next to the city basically. You can see the background, there's a mountain, but that's it. If you look in the other direction, it's just the whole city is there. So we can't do anything that's spread out like galaxies or nebula. The sky background is too bright, so we had to basically concentrate on point sources, and all of these are basically, well, except for the moon, but the stars and asteroids are basically point sources, so that's why we chose to do this kinds of observations. Next one, please. Okay, for those of you that have been into astronomy but hiding in a cave for the last 10 years. Transits of extrasolar planets, what are they? So this is a very, very summarized version of what they are. Basically, extrasolar planet is a planet that goes around another star. And when the inclination of the orbit is such that basically 90 degrees to the plane of the sky, the planet can cross in front of the disk of the star as seen from the Earth. When this happens, the brightness of the star dims just a little bit, less than 3%, and basically that's what we are observing, that's what we're measuring. Depending on the size of the planet, that would depend on how much brightness brightness decrease there is. So the larger the planet, the more of the star it occults, and therefore the bigger the magnitude drop would be. And it's the only method that can show us basically the size of the planet using this methodology. And there are over 1,100 planets known outside the solar system, but actually there are many, many, many more. And there are a lot of unannounced discoveries yet. We decided not to go into the business of trying to search for them because that's a whole other ball game. That's basically searching in the dark with a lot of equipment, and we just didn't have the resources. So we decided to look at the known planets and the known planets that transit and try to characterize them better. And the reason is, if you look at the discovery papers, usually they rush to announce the discovery of a new exoplanet, and sometimes there are not that many good quality light curves in the original paper. So there are some uncertainties about the size of the planet and the characteristics of the system, and they go on to the next discovery. So and sometimes some of the systems get left behind. So this is sort of a way of trying to cover that gap and try to characterize systems that have not been observed a lot, or that are not very exciting or sexy or something. So that was sort of the reasoning behind it, the logic behind it. Next one, please. And it's all geometry. It's actually rather simple geometry. It's a transit of Venus, except the planet is a little bigger. And you basically have a disk, that's the star, and the smaller disk that will cover the light from the bigger disk. And depending on how the planet crosses the front of the disk, whether it's through the middle or through near the edges, you will get different light curves or different shapes of the way the light diminishes when the transit occurs. So fortunately, several people have worked out the geometry of this. Some of the equations are there. Next. If you have a rather central transit, then the transit will be longer and the slopes of the ingress and the egress will be also sharper. Next, please. If the transit is near the edge, so it's not central, it has what is called an impact parameter, or the distance between, the closest distance between the center and where the planet crosses, then you will have shorter durations, and also the slope will be more gentle as it comes in and comes out of the transit. But the depth of the transit will be the same in both cases. And so there have been a lot of people working on this, on the geometry, and there's actually a lot of software out there that can do the modeling for this nowadays. The next, please. And basically, those that are marked by the boxes are the most important parameters you can get out of the light curve. There is the inclination of the orbit of the planet on the left, and then on the right, there is the size of the planet, the radius of the planet, with respect to the radius of the star, and also the distance of the planet A in terms of the radius of the star. Those two are in terms of the radius of the star, basically, or the sun in the case of the radius of the planet, because we really don't know what size the star is. The size of the star is so far a model parameter. There are very few stars we can actually measure the diameter, and they're not very well measured, some of them. So besides the sun, that's it. We still have to leave all the uncertainty on the respective size of the star. And usually that ends up being sort of a limiting factor here. There are very good models about sizes of the star based on the temperature, the specific gravity, the metallicity of the star, and other parameters. But they're still models, so it's still not an independent variable you can measure. So basically all this is to saying, if you're good at geometry, you can do this. I'm not good at geometry, so I had somebody else do it for me. Next.
You're in good company.
So, well, a little bit about the characteristics of the extrasolar planets that have been found so far. Basically, you find a lot of exoplanets around main sequence stars, like the Sun, with relatively high metallicity. So the figure on the top right over there shows the metallicity of the host star, 0 being the metallicity of the Sun. It's a logarithmic scale. Negative numbers, it means it's a metal poor star. Positive numbers is a metal rich star. And you can see they're pretty much clustered around the Sun. So that's kind of not very surprising. It'd be surprising if the stars were metal poor and we would see a lot of planets around metal poor stars. That would be something surprising. So this is sort of expected.
Could you say just a couple of words about the meaning of metallicity and astronomy?
Oh yes, astronomy has very simple chemistry. There's hydrogen, there is helium, which is gas, and everything else in the periodic table is called metallicity. And basically what they do is they look at the spectrum of the star and measure all the lines that are not hydrogen and helium and compare them to the Sun. If there are more lines or stronger lines of those, what we call metals, then it's a metal-rich star. It has more heavy elements were included in the nebula that formed that star. So our Sun is a second generation or maybe third or fourth generation star. So it has a lot of contamination of heavy elements, anything not hydrogen and helium, from other stars evolving, exploding as supernovas or just as red giants. So basically what this graph is saying is that you need to have second and third generation stars in order to have higher probability of planets. We haven't found too many stars that are metal poor or first generation stars with planets. So that's sort of an interesting discovery in itself, which was sort of expected. So it's one of those things that you're surprised but not that surprised. So that's about metallicity. Did I cover what you wanted to say, or did I not read your mind properly?
No, that was perfect. It's just some people here may not be familiar with that term.
Yeah, please do stop me if I go too far with my jargon or too low with my humor. Anyways, the planets have come in different sizes. Bottom left, you can see basically planetary mass of the star versus planetary radius. And you can see that they're starting to cluster. You see planets that are, like the mass of Jupiter, for example. The yellow circle is centered more or less on the mass of Jupiter. And the sizes are a little bit bigger than the size of Jupiter. 1 is the size of Jupiter, 10 to the 0 is 1 is the mass of Jupiter. So those are basically Jovian planets. But then there is another sort of group of planets, the blue ones, which could be called terrestrial or semi-terrestrial, or they're smaller. So there's starting to be a segregation of planets. Like we know in our solar system, we have giant planets like Jupiter and Saturn, and we also have terrestrial planets like the inner solar system, and we also have sort of mid-sized planets. Anyway, so it's sort of a reflection of how nature turns out planets, I guess.
Question?
So we're starting to have enough statistics.
We have a question?
Yeah.
Yeah, do I have to come up and talk? Yeah, are the masses for the small planets, are those from spectral data or something else?
Did you hear that?
Yes, that's a good question, because I've been talking about transits, and transit is only the light curve, but you also have measurements of what we call radial velocity of the star. When the planet goes in front of the star, it basically pulls the star towards you a little bit. When it goes behind the star, it pulls the star away from you a little bit. And you can measure that wobble in the spectrum as a change in velocity. And that changes in velocity is reflected in the spectrum as a slight motion or displacement of the absorption lines of whatever element the star has. To the red if it's moving away, a red shift, or a blue shift when it's moving towards you. And the more massive the planet is, the more it pulls on the star, depending on its distance. And you can measure that pull, and you can actually calculate the mass of the planet based on the radial velocity alone.
Oh.
So the transiting planets are really cool.
Follow-up question.
Yeah.
Yeah, just a follow-up question. I don't remember offhand, but where is the Earth on that? Is that below 10 to the minus 3 Jupiters?
Something like somewhere around here.
Okay, so
Oh yeah, I'm I'm trying to use my cursor here, but it's not working on your screen. It's like the first or the second dot on the bottom left.
okay, so we are getting some Earth mass, but most of them are much bigger.
Yes, most of them are what we call Neptune-sized planets or Jovian-sized planets. Earth-sized planets, very few we've found, and those have been thanks to Kepler, because since it's outside the atmosphere, it can do transits really well without any atmospheric interference.
Okay, thank you.
Sure. So where was I? Forgot. Oh, anyways, planets come in varying sizes, and what's surprising is the last 2 points over there, which is basically that we find solar systems that have very eccentric orbits, and some of them have orbits of the planets that are very close to the stars. In the bottom right figure, the red circle is the planets. The green line is, what is it? T is, I didn't change this, it's still in Spanish. J is for Jupiter, that's the 5 astronomical units. T is for Tierra, which is the Earth. Anyways, and I think M is for Mercury. So Mercury, Earth, and Jupiter. And you can see some of them, there's a bunch of planets that is really, really close to the stars. We call those hot Jupiters. The ones we found are very hot in temperature because they're really close to the star, but they're also very massive. They tend to be like Jupiter, or maybe 2 or 3 or 4 times as massive as Jupiter. So those are really interesting planets because those are the first ones we found. But we also realized that that was a selection effect. The massive planet close to the star will make the star wobble back and forth much stronger. So those will be the first ones we notice. They're not necessarily representative of the entire solar system. However, it's still interesting. How did a planet like the mass of Jupiter or Saturn end up being in an orbit which is like, 5 times closer to the star than the orbit of Mercury? So we've had to really figure out some theories of how to migrate a giant planet from its formation area, which is several astronomical units away, that close, and then stop it just in time before it hits the star. Because if we have some device like friction or whatever, you can carry it all the way to the star and make it disappear. But now you can see there are a lot more planets at the distance of the Earth or Mars, the blue line. And that's, again, thanks to the Kepler spacecraft that can look at planets that are smaller and also farther away, turns out farther away from the star. Because Kepler doesn't rely on radial velocities, it relies on just looking at the transits of these planets. Also, you have to think that the farther away it is, for example, if it's at the distance of the Earth, it takes like a year to go around for a transit. Whereas the ones in the red circle, those are so close, you can get transits like every 3, 4, 5 days. You can get the planet go in front of the star. So the ones in the red circle are my favorites because those are the ones I can really study, and if I miss one, I can look at it 5 days later and catch another transit. Whereas the ones around the Earth or Jupiter, you only catch them once a year if you're lucky. And if it's cloudy, that's it. You didn't get anything. So again, thanks for Kepler for being out in space and there's no clouds out there. So eccentric orbits, I didn't put a graph, but that's also sort of surprising because our solar system is nicely well behaved, has round orbits, a little eccentricity here and there, but all the planets are distributed nicely. Nobody is, bumping against anybody else. But in this solar system, some of the orbits are very eccentric. And if you have a giant planet in an eccentric orbit, it plays havoc with whatever terrestrial planet you want to have there. So there have been very interesting dynamics that are inferred from the fact that you have a lot of extrasolar planets with very eccentric orbits. Basically means there should be a lot of wandering planets out there in space without a star that have been ejected from their star system. So those are the general characteristics of the exoplanets I wanted to sort of talk about a little bit. Any questions? While I catch my breath.
Everybody's shaking their head no, so either
Okay.
they understand all this or they have no clue what you're talking about.
I hope it's the former, not the latter, excuse me.
I do have one question. Dr. Sada, when you talked about the size of the disk of the star, that's not something you can see, but it's something you infer mathematically then, right?
Yes, there are a lot of people that work on stellar modelings that model the inside of stars and their evolution through the HI diagram. I'm a little afraid to mention it. You know what the HI diagram is? The Hertzsprung-Russell diagram? I don't have a figure, so I'm a little scared to bring it up. it's a whole other lecture. It's really fascinating. So if you want to invite me again, I can talk to you about the HR diagram.
Okay, that's fine.
We can cover that later.
Yeah.
Okay, but basically, yes, there's a lot of people that work on modeling stars, and they actually carry the star through this entire life from almost beginning all the way to the end, and try to reproduce what the star would do, you know, how it would become bigger or smaller, the temperature would change, the nuclear reactions in the inside would change, and that basically defines a star that has a certain mass and a certain temperature to have a very specific size. And those are the models we use here in all this modeling of the extrasolar planets.
Very good.
And as much as we would like to believe that those models are right, we still have to carry that little, you know, radius of the star in there in all our calculations. Whenever we can send spacecraft and actually measure the radius of the star, then we can take that away from the equations.
Very good. Thank you.
Okay, so the next one, this is where I get to brag. These are how many extrasolar planets I have observed. The numbers has been 431, and that's actually current. 401 of them have been total, which means ingress plus egress, and 40 have been partial because of clouds or whatever. Of those 401, 274 have been of really good quality. Well, okay, at least I like to believe so. And I have observed 83 extrasolar planet systems. So I have observed, for each of those 83, a lot of them I have observed more than one transit. The observatories I've worked in, UDEM is Universidad de Monterrey, that's where I worked, 333. KP is Keep Peak. Visitor Center is 57. The 2-meter telescope is 44, and the McMath Piers and others telescopes, 7 transits.
Yay, McMath.
And these are the filters I have observed through. And the filters are important because if you look at the diagram there of hat P12, the star is not flat. The star is what we call limb darkened. Towards the limb, it's a little darker because the light has to cross more atmosphere to get to us, more atmosphere inside, just around the star, not our atmosphere. And that limb darkening is very, very dependent on what wavelength you're looking at. If you're looking at short wavelengths like blue or green, the limb darkening is very pronounced. Just, you know, look at the sun and you will see how limb darkened it is. Well, don't do it now. But if you work in the infrared, the longer wavelengths, that is much less conspicuous. It's flatter. And so that is important because the ingress and egress, as you see there in the model, as the planet goes in front, is not like in the previous diagram when I showed the mathematics. Is not a straight line. It's a curve, and that curve depends on that limb darkening. So the best information is observed if you look at several wavelengths. But if you're looking for the size of the planet, then you want to look at long wavelengths. So that's why we use the 2-meter telescope to look at transits in the near infrared at 1.25 or 1.65 microns. As far red as we can get, because the redder we look at, or the longer wavelength we look at, the limb darkening is less of a constraint, is less important. So you can get a better size of the planet the redder you look. And also the redder you look, the atmospheric turbulence is less. If you look at in B or in V, the star basically twinkles a lot. If you look in the infrared, it twinkles less. If you look in the near infrared, it twinkles less. So it has its advantages. You get less atmospheric turbulence, and you also get better estimation or uncertainty of the planet size. The problem is that the longer wavelength you go, also the star becomes dimmer. Unless it's a red star or something like that, the star is dimmer, so it's a trade-off. So basically, and the next one, please. And that is the statistics of the number of transits from 2005 when we started until 2015, which we're probably finishing this project this year, mostly because we've had such crappy weather here in Monterey. I mean, I gave this talk a month ago and I haven't observed a single transit since then.
Wow.
It's just been cloudy every day, and the day that's not cloudy, it's so humid that the telescope just, fills with water. So you can take El Nino and global change and all that. But anyways, in blue are the ones we've observed, in red are the ones I've observed in other observatories. So those are my bragging points.
Wow.
Next one, please. Okay, and this is the methodology I use. The idea is that with a small telescope, you get a very noisy light curve. So the idea is observe several light curves and combine them together and then analyze it. And so this is more or less the procedure that I use. First is the individual observations of the transits from the observatory. You have to frame the field of view to maximize the number of comparison stars. You have to choose it so every time you have the same comparison stars. So you can't be changing the equipment too much or the comparison stars too much. You want to use the same ones. You also have to make sure to observe 1 hour before the ingress and 1 hour after the egress, so that you get a baseline of what the brightness of the star is outside of the transit. Very important. And also, you have to look at stars that are above 30 degrees in the altitude.
Could you spend just a moment explaining the importance of and what a comparison star is used for in photometry?
Yes, the comparison star in photometry, if you want to briefly go to the next one and then come back. There you can see there, this is a field of view. On the left is the actual image, and on the right is my, software program, planning software kind of thing. So that's WASP-10 observed. The red star is actually the target star. That's WASP-10. WASP is an acronym for the Discovery Project. I don't remember what it is. But anyways, and that's the red star. The green stars in the with the green circles are the stars that are used to compare the brightness of with the red star. Basically, in photometry, what you do is count the number of photons, if you wish, of your target star and compare them to the stars that you know are fixed in brightness. We call those comparison stars because we use them to compare the brightness with. And if the target star changes brightness, it will change brightness with respect to those stars. And you want to use stars that are in the same field of view, in the same picture, because if there are slight absorptions due to the atmosphere, then all the stars get affected more or less the same. As the stars rise and set, the closer you get to the horizon, the more absorption from the atmosphere, and so the brightness diminishes for all the stars. So, your target star would diminish just because more photons are being absorbed by the atmosphere, but so will the comparison stars. So you compare them to those comparison stars. They're affected more or less the same way. And so that's why we use those comparison stars. You can see there are two stars that are way too bright to use as comparison stars to the bottom left. So you can't use those, for example. So, is that okay?
Yes.
Thank you, Pedro.
Yeah, if you go back one, please. And if the stars are too bright, you might also want to defocus. So that's the second point over there in the point one in methodology. The second item is a slight defocus and use the same exposure times. This is also tricky because you have a small telescope. You want to spend all your time counting photons and not downloading the information from the CCD. So sometimes the readout times of the CCD is like 30 seconds. Well, those are 30 seconds wasted. 30 seconds you didn't count photons, you were just downloading the information to your computer. So we do binning, and we do longer exposures, and sometimes we also have to defocus the stars slightly. Sometimes I'm even doing photometry on donuts, not just defocused stars. You can actually see the secondary in there. But that's okay, we don't want pretty pictures. We want the count of photons to be reliable, and the more the photons, the better. So that's what we do. And there are other considerations for observing. Point number 2 is light curve reduction. We have to reduce the data. So we have to use some photometry software. In this case, I developed some software I use myself for IDL, which is a programming language. And basically, you compare the light brightness of your star with the brightness of the comparison stars. And you use an aperture, which you can vary in size. So we vary the apertures to minimize the scatter and the final light curve. Basically, that's our criteria. And use the same comparison stars. And we also fit an air mass dependent function to the portion of the light curve outside the transit and correct. Okay, if you can go ahead 2 slides. This is what a regular light curve looks like initially. And you can see on the left side, yes, on the left side, around between 3 and 4 hours universal time, it's kind of low. So if you see, I think it's a pink line there that goes from that side of the transit to the other side. That is the reason you want the baseline before and after. There is a thing called atmosphere, what's the name? Anyway, as the star is lower in the horizon, it's called differential, I forget the name. Alzheimer's moment.
Absorption?
Differential extinction. The closer you are to the horizon, red stars or blue stars are affected more by extinction than red stars. The atmosphere in our sky basically scatters blue light better than red light. So blue light gets lost easier on the way from the star to the Earth, to the telescope across our atmosphere. So if your comparison stars have different colors, different temperatures, you will get this differential extinction issue. Plus there's also light pollution issues. Some part of the sky might have light pollution compared to other part of the sky. So what we do is fit a model that depends on air mass. Air mass is an amount of air you look through. The closer to the horizon, the more air mass you're looking at. And if you click the next, and that's already corrected. So we fit a function to get rid of that air mass problem. It's an empirical function, but it works well in about 80% of the cases. In the other 20% of the cases, we just use a linear function because we don't know what else to do. So you got to do something. So that, if you go back 2, please, or one more, there we go. So in the light curve reduction phase, you have to take into account things like that. Now, so you get the individual light curves then, and then you combine the individual light curves. And this is a little tricky. First, we fit a preliminary model, and that's the software we use. That's a commercial software you can buy, Binary Maker 2. And it works for double eclipse and binary stars. So you have 2 stars that go around each other, and one goes in front of the other one. So this software basically does exactly the same thing, but what I do is make one of the stars really cold and really tiny, basically. And it works great. And it's even, you can, the way it works is that the stars themselves are divided into sections, and you can put star spots if you want in them. You can put cooler sections of the star than others. So you can actually have the planet go in front of star spots and see how it behaves. So it's a really nifty little software piece that you can also use for extrasolar planet transits. But anyways, this is just a sort of a preliminary model. I do it, and I basically get the center of the transit. What time did it happen exactly? The middle of the transit, the middle of the, we call that TC, okay? And we align them on that TC. So after we find what's the central time for those light curves, we average the individual light curves and obtain a combined light curve out of that, okay? So what we do is we take a 2-minute time interval, a bin, and then whatever point lies within those 2 minutes, you average it, and you reduce the noise quite a bit by doing this kind of averaging. So, and then you can go ahead and fit the model to that combined light curve, and then use that model to refine the individual central times of the transits and iterate that process. So basically we have an initial model. That model we fit to the individual light curves. We find the central times. We combine them, get a master combined light curve, and then we get a model that fits that combined light curve, and then we use that model to fit the individual light curves again to sort of correct the central times, and then we do that a few times until we iterate to the best solution. Okay? And also in the process, we have a lot of individual transits, and we can calculate the period of the system, how long it takes it from one transit to another, the exact period of the orbit of the star, of the planet, I mean, around the star. So that's another thing we derive from here. So, so you combine the light curves, and then the fourth step is the modeling of the combined light curve. We have to assume some parameters from the literature, like the temperature of the star. The gravity of the star basically is a measure of how big it is, log G, so you proceed to ignore it. Fe over H is the metallicity of the star. Those are all model parameters that you get from spectroscopy, basically. We use limb darkening. Remember I mentioned that? Well, those are also modeled. So we get, there are several ways of modeling how the light of the star diminishes towards the edge of the star or the limb. And in this case, we use coefficients, A and B. And then we use the orbital parameters, the eccentricity and the angle of periastron, E and omega, from the original paper. So the first modeling approach is to get the parameters that we cannot get, that we don't know because we get from spectroscopy, we get them from the original paper or from models, and we use that to model. We use a software called Exoplanets, which is also for IDL, which is a programming language. And we get the radius of the planet compared to the radius of the star, the distance of the planet to the star compared to the radius of the star, and the inclination of the system. And we can also even go a little further. This modeling software can let us actually calculate not only those parameters, but also if we have radial velocity data from the literature, or you have your own spectrograph and big telescope, you can get radial velocities, and you can also calculate the orbital parameter E and omega, which is the eccentricity and the argument of periastron of the star. So that's sort of the methodology so far. So the observations, the next page, I already talked about. Nothing in this, the big square here is my field of view, and the top square, the little one, is actually the guide camera. So you can see there, I actually put the guide star in the corner, in the bottom left, the right corner there, to guide on that star. And and the big circle there, or the big annulus, is how you can rotate the camera on the telescope if you want to.
What kind of typical observation times do you use, integration lengths?
Shortest is about 15 to 20 seconds for the really bright stars, like 8 magnitude. And longest, I don't like to go beyond 3 minutes, because then you start getting into guiding issues.
And what kind of magnitude do you reach in a few minutes like that?
My sweet spot is around 12th or 13th magnitude. That's sort of the best. I can go to 15 if pushed, but not beyond 15. It also depends on the filter. If I get to 15th magnitude, it's like unfiltered basically. Which is not very useful. I mean, you get all the photons, you get a nice light curve, but you don't have much control over what wavelength you're looking at. So I rather use filtered, even though it knocks out more than half of the light. And the next one was the different, what's it called? The differential extinction. Next one. And the next one. So these are the results. So that was the whole methodology. Maybe I should pause here and see if there's any questions about the methodology, because the rest are results.
Any? Everybody's shaking their head no, so
Okay.
let's move on.
We believe you.
We believe you.
I feel like I'm in class. Everybody is very quiet and attentive. It's like, oh my God, they're understanding everything or nothing.
So what is this O minus C value?
We had a question of what is the O minus C value?
In here, okay, well, let's get into the results. Yes. The first graph here is for the first system. I'm going to show you 5 systems because those are the 5 we've analyzed so far. HATP12. The x-axis is Julian date, is just basically the date. And the y-axis, O minus C in seconds, is observed time of mid-transit minus calculated time of mid-transit, giving a fixed period. So if you have a period of 3.2130589 days, like we have over there at the bottom, and the central time for the first transit, T0 of whatever Julian date that is, so every time the period is repeated, it's basically 0. So any deviation from 0 is how early or late the transit was observed from the predicted fixed period. The open diamonds are literature or previous observations, and the filled in black circles are my observations. The uncertainty bars are 1 sigma, 1 standard deviation. So if you want to be really truthful, you have to multiply them by 3 to start thinking that it's a significant deviation from a fixed period. So if you take the one on the very right of my observations, the latest one, you can see it's kind of a large uncertainty, but really you have to multiply by 3 and then see if that is significantly different from the 0 point, basically. So that's what this whole graph means. Why do you use it? Because you can find here if there was any trend that the period was getting shorter or longer, you would notice it here because this assumes a fixed period. If there is another planet in the system that's gravitationally perturbing the first planet, the one that transits, you would see it here too. When the timings of the central transiting are varying. In this one, you can learn 2 things. One is that really there is no significant deviation from a fixed period, i.e. there is no planet perturbing it, or there is no change in the period for whatever reason. And number 2, that astronomers tend to be very optimistic about their uncertainty values. Because some of those are really tiny and I don't believe them. So,
And they're all correct.
so basically HATP12 was a regular system. We observed 1, 2, 3, 4, 5, 6 transits. Next.
Corrected for the
And those are the 6 transits on the top. So on the graph, you can see the date and the transit, and the raw data are the points there. I didn't put any uncertainty because then it gets too cluttered. And the bottom one, the bottom curve is the combined light curve. as you can see, the scatter is much, much, much less. That's the point of this whole exercise. You have a small telescope, you have data that, not many photons compared to a big telescope, so your data is going to be ratty, it's going to have scatter. Well, how do you fix it? By, observing a lot. And a lot of the times you observe the same transit, and then you combine the data, and then you can get the modeling. On the right, you see the model results. The radius of the planet compared to the radius of the star, 0.14. The A over R is the distance of the planet to the star in the terms of radius of the star, 12. So it's really close. I is the inclination. E equals to 0 means a circular orbit, basically. That was obtained from that reference, Knudsen et al. 2014. And Hartman et al. 2009 is the first reported data for this. So as you can tell, we're basically getting the same numbers within the uncertainties. So we're very happy with that. That means our methodology works. You can combine a lot of transits from a small telescope and make people believe that you're using a big telescope. And then, so this was basically to try to make sure that the methodology was sound, basically. So this one, the first one, so we give it a smiley face. The next one had P13. Now this is an interesting system because there is a planet, a second planet known in the system. Okay, so this is two planets, only one of them transits, the other one doesn't transit. It's further away, and any slight inclination of the orbit, the farther away you're from the star, the larger the chance it won't go through the disk of the star. But unfortunately, this is a really big F star, so it's big, it's hot, it's bright, and even though the planet is big, compared to the size of the star, is still a very small brightness decrease during the transit. So the transits are very shallow. When the transits are very shallow, it's very hard to predict, or actually it's very hard to measure the transit, the central timing of the transit. Is very hard to do. And that's why they have very big uncertainty lines. Notice the O minus C scale is now up to 700 or 800. So that is because it's a very shallow transit. And here supposedly is a signal of the other planet mixed in. Unfortunately, the signal of the other planet causes the timings from the fixed period there, which is 2.9 days, it causes them to vary by 3 or 4 minutes. So 4 minutes, but let's make it 5 minutes if you're generous. That's how many seconds?
300.
500 seconds?
300 seconds.
300 seconds. So basically the size of the uncertainty bars. And again, these are 1 sigma, not 3 sigma. So we cannot see the second planet here, although we do see it with radial velocities. So this is much easier to measure the secondary planet with radial velocities. The next slide, please, shows the light curves. You can tell they're really shallow. So first are 4 of the shallow transits I observed. The next one shows another 4, and then the combined light curve. Okay, you can see, for example, in the March 3rd, 2013, right there, the middle one, you can hardly see that the brightness diminished during the transit. But in the combined light curve, you can see it really nicely. It's a very long transit. The x-axis is in days from mid-transit, so 0.05 days. Oh, sorry to use strange units, I should use minutes, but anyways, it's like a 4 or 5 hour transit there. So it's a very long transit, and it's very shallow, very gentle, the ingress and the egress. So that's why it's really hard to measure the central transit time. So for this one, we use the eccentricity and the angle of periastron from, again, Knudsen et al. 2014. They did a very good study about the radial velocities on a lot of the systems. And then above it is our measurements compared to Backus et al. 2009. And again, you can see they're pretty much the same. So again, we got away with, playing with small telescope and pretending it was a big one.
Yeah, it's good.
So this is another one that we actually got the same result as the initial ones. Next one, please. HAT P16, is it? Yes.
Yes.
HAT P16 is another one. We only got 4 transits for this one. It's a lot of scatter here, but there are too few points to start figuring out whether there's a period or not, or a variation from a fixed linear period of 2.775 or 6. So the next one, might as well jump into the results. There are the 4 light curves. They're really nice. The combined light curve is really nice again. And the results, again, match those of the original paper. This one we actually also calculated the eccentricity and the angle of periastron, and we get almost exactly the same results. So I don't see any major deviations, maybe the inclination a little bit, but remember 3 sigma, not 1. The distance, no, everything seems to be about the same. So again, we're very happy. Our methodology works. You can use a small telescope to get real science out of things. The next one, HAT P23, my favorite. 1 point in the literature way back in 2009, and the rest are ours. This is one of those neglected ones I was telling you about. There are 2 points that are really far away from the 0, but everything else seems to be okay. So this is a very, very short period. It's 1.213 days. So imagine every 1.2 day going around the sun. That's really close. This is what we call an inflated hot Jupiter. It's so close that the size of the planet is bigger merely due to the temperature. It puffs up the planet, literally, compared to hydrodynamic equilibrium at colder temperatures.
What kind of star is the host star?
Oh my God, I don't remember.
A bright thing.
It's not very, well, it's magnitude 13 or something like that. It's not very bright. Apparent magnitude, but I don't remember the spectral type of the star.
Okay, I was wondering if it might be a red star to even exaggerate the ease of getting the transits.
No, it's a main sequence star, so I do know that. So it's not big. Let's call it solar-like. Anyways, the next one shows 1, 2, 3, 4, 5 of the transits over there. And I think if you click it again, shows the other transits. There we go. There's the first 6 and then 5. So 11 transits for this one. And you can see all sorts of transits. Very large scatter. But then the final light, combined light curve is really nice looking. There's a little wiggling in there. And I think I know what that is due and how I can get rid of it. But this one was interesting because we actually get a different result. If you look at the size of the planet, we get that the planet is about 5% smaller. Now, if you 0.1118 plus minus 0.001, as much as you wanted to make it 0.1169, you can't. So with similar uncertainties, we do get a planet that is, well, it says they're 4.5% smaller plus or minus 1%. So there were some models that were expecting this planet to be smaller than what was measured initially. Fortney et al. Mentioned that maybe this planet should be a little smaller. Anyways, the distance and the inclination is the same. We also improved on the eccentricity and the angle of periastron. You can see it's basically the same numbers for both, except we cut by half the uncertainties. So this is one instance in which we actually got some results that were a little different, that had to defend the fact that they were a little different. Some people are saying that this method it's a little tricky because if the star is variable or it has star spots, then some of the transits can be affected while others are not affected. So you have to be very careful when you combine the transit from different times, because there's no guarantee that the star was behaving the same way as in previous or later transits. Maybe it was misbehaving. And in some of these cases, you can't tell. I mean, you can see the scatter is rather large in this one. But anyways, so it's also an agreement with a previous paper we actually published on this one that we only use the first 4 transits from the previous. And then we got more transits of this ones, and we reinforced our initial solution.
One question.
And next one.
Question?
On the slide with
Okay.
23B, the second transit, the plot is missing data on the right half of it. Is that a cloud? Is that bad seeing?
Yes, that particular one was clouds. Yes, I was observing, everything was happy, and then all of a sudden clouds came, and I started cussing.
Yes, yes.
And those usually have very large uncertainties on the central time, because you only get one side of the light curve. You only get the
yes.
ingress. The most important part here is, I would say, the hour around ingress and the hour around egress. That will basically define everything else. The middle of the transit, you can live without it. As you can see, the one above it, on October 4th, there's a lot of gaps there because that was partly cloudy. But you need the ingress and the egress to be happy.
Very good.
But I decided to put it there anyway because, I can't be picky and choosy about it. I have to take the lumps and just, use all the data.
Great, thank you.
Next. And WASP 10?
Yes.
That's another nice one. This one has been observed a lot. I'll show you why. Again, the diamonds are literature and the black dots are my observations. You can also tell the lag of how long it takes for stuff to be published. If I'm publishing this in 2015 and the last observation was published in 2010 or 2011, that means that some of this takes 2 to 3 years to see the light of day. Anyways, this one also shows basically linear. I mean, there are a couple of points here and a couple of points there. Maybe some people don't synchronize their clocks. It's very important to synchronize a computer clock and keep it synchronized with universal time. Some people use heliocentric times. There are different ways to measure time: dynamical time, universal time. So you do have to be very aware of how you're measuring the time for each exposure. And some people sometimes miss a little bit, like the 2 points in 2009 that are really below. I don't know what they were looking at or what their clock is, so I have to take it at face value. Okay, then next one, please. And that one shows the first 4, no, those are, yes, the first 5. This is a very nice system. It has a very deep transit and very sharp ingress and egress. And it's a bright star, and the comparison stars around it are really nice and well behaved. So this is one of my favorites. If you can see, the next one is 4 more transits and the combined light curve. You see the combined light curve, really nice, the model there. And the data, as you can see, matches basically, in this case, Johansson et al. 2010. Our observations are almost identical. Almost, you could even think it was the same guy doing it. But I swear, that's the way it came out. We also used radar velocities. This one apparently has a long-term variation in radar velocity, which suggests a very far away planet. So we couldn't do radar velocity calculations ourselves, but we got the Knudsen et al. Data there. And it's an agreement with a bunch of other people, and not so much with one guy that just got something out, which I'm still scratching my head why that is. But anyways, so that's WASP 10. And the next one, I think, is my favorite. in the sense that on the right, you have our observations of WASP-10, and on the left, the University of Hawaii 2.2 meter telescope doing one transit. So, see, I mean, with a small telescope, you can get data that is, looks like a grown-up telescope.
So University
The
of Hawaii
variation
spent too
is
much
very
money then.
small in both light curves. If we get a couple of light curves for
So there was a
WASP-10,
comment here that apparently the University of Hawaii is wasting a lot of money.
well, yes and no. Yes, in the sense that, how can I say it? They did one night of observation. We did, 10 nights of observations? 9 nights of observations for this one. So,
So are you
to be
saying
honest,
actually
I'm
that
getting
you're-
one night.
Are you actually making the claim that your signal noise scales fairly well if you compare the aperture to observing time and get the equivalent collecting power that way?
Almost. Theoretically, you could get square root effect. So for every, if you combine 4 transits, it should be 2 times less scatter. If you combine 8 transits, whatever, or 9 transits, which we did is 3 times less scatter. But we also have to take into account that we are working from a suburban telescope. University of Hawaii is working from the best site in the world for seeing and stuff like that. So we're not quite there. And after 8 or 9 transits that you record, then you hit the point of diminishing returns. You would need like 20 transits to see any marked improvement. So the best we can do is try to imitate what a big telescope would do in one night. But that would take, like I said, between 6 and 8 or maybe 12 transits, depending on the system and your individual conditions. But there's a point in which, yes, you paid one guy to observe in a 2.2 meter telescope, but if you pay the salary for one night, instead of paying it for 9 nights, the salary. But then the operation of a 14-inch telescope is much cheaper than a 2.2 meter. So it's a lot more work, but the results are the same. So
Wonderful.
what I'm basically saying is that this is a very good way of having a small observatory like you have. I mean, the 14-inch, I'm sure some of you have even bigger. But if you choose a project and stick to it, you can actually do grown-up work with it. It takes longer, but it's really nice. At least for me, it was a very interesting learning experience. I didn't know anything about extrasolar planets. And now I feel I know a little bit more. The next one, please. Next one shows the results. Next. So check mark means that we actually got the same results of the literature, which validates our system. And the next one, basically that's our only difference right now that is significant from anybody else in the results. And you can see the light curves. They come in all shapes and sizes. The WASP-10 is very nice and deep. HAP-13 is very long and very shallow. And there's everything in the middle. Okay? Next one. And actually, using the observatory here, Universidad de Monterrey Observatory, all those publications have some of my light curves. I've used some of the light curves to actually complement or supplement, I'm not sure how to say it, observations from Spitzer or from other telescopes or other observatories. So some of those, as you can see there, are Spitzer, or yeah, most of them are Spitzer, I guess. But anyways, it's interesting. The last paper you see over there that says "En preparación," which means in preparation, 2014. Today I got the referee report, and he liked it. He wants a couple of things done to quantify better the scatter and some of the expected numbers and how I got that stuff. but it should be out this year. So I woke up with a smile about that today.
Good.
Next. And what is there to do? Future work. Well, all those systems you see there, I have a lot of light curves pending. About 50 light curves, I will combine them to get, again, the period, the size of the planet, the distance of the planet to the star, the inclination, the eccentricity, and the angle of periastrum for all those systems over there. I have 5 or 4 light curves, or 6 or 7, some of them, and those are the filters. So if you look at the previous one, the exoplanet transit, the paper, I call it part 1. I mean, part 1 is the one before that. That's the one I got the referee review. And I'm working on part 2, which is basically this other ones. And the next slide. Those are the ones I'm working on. So there's going to be another paper coming out with monochromatic light curves. And then the next one, interestingly, a lot of them, well, not a lot, 4 of them, I have taken so many light curves that I changed filters. I've observed them through visible, red, infrared, and mid-infrared filters. And so what I'm going to do is a comparison and to study the limb darkening coefficients A and B. Are they really working? Can I tell anything about limb darkening, differences between model and theory? Or can I just see the differences between one color and another color for the same system? So that's going to be another paper. And the next one is some individual cases of interest. HD 189733, I have a lot of different ones. Notice the last one is a HA, means hydrogen alpha. That was a mistake. We were supposed to be using a different filter, and the filter wheel got screwed up, and we got a nice H alpha. We were looking at the chromosphere of the star, and the planet went in front of the chromosphere of the star. So there are a lot of wiggles there. So nobody had thought about looking at, narrow band wavelengths and narrow band filters and looking at that. So that mistake actually is going to pay off. HAT-P4 is a very long transit that has very shallow transit too, longer than HAT-P13. No data is in the literature from that, and we have a lot of nice transits. And well, the other ones are also interesting because 1 or 2 things. In GJ 1214, actually, it's one of those ocean planets, they call them now. That's super Earths, that's another name for them. HAT-P3, I'm working with somebody else here in Mexico on it. We are combining light curves from a bunch of telescopes. And the next one. There you see HAT-P13, it's a big star, very shallow transit, and WASP-10 is a smaller star with a very nice deep transit. So those I just put there for contrast, so you can look at them, meditate, and see if you have any questions.
Thank you. Well,
Thank you.
Earthquake in California?
Yeah.
I have one
There.
quick question. Do you actually switch the
Questions?
filters during a transit, or
There'll be an
you?
exam tomorrow.
I think the question was, do you actually change your photometric filters during a single transit, or do you stick with a single filter through each transit? Is that the correct question?
At first, I changed filters. I would take one filter and then rotate the wheel and take another filter and go back and forth. And then I learned that my filter wheel isn't that accurate, so I couldn't flat field them properly. So ever since, I'm just sticking to one filter for one observation.
And then you just arbitrarily pick the 50% point on the slopes for the
Actually,
time?
sorry.
Then you
For the
pick
time, just pick the 50% point arbitrarily on the
you
slopes?
pick. He's asking, do you pick the 50% point arbitrarily on the curve?
Right.
The 50% point?
Well, for the
What do you
time,
mean, the middle of the
For the getting the center time point.
Right.
Do you?
No, I use a model. I use a model basically to fit the model to the data, and that gives me a central time.
no,
Another way of doing it is to take arbitrarily choose a center point and fold the data. If you have a middle point, then you fold it back into each other. They're supposed to be symmetric. And then you move that center point until you find which is the best fit for a symmetric one. That's another way of doing it. I've done both. It's basically the same.
Thank you, Matthew.
Hello, thank you for giving this talk.
Sure.
How close would Jupiter have to be to our sun in order for it to push and pull? Like if there was another civilization looking at our sun, would they be able to measure the pushing and pulling of the star that you mentioned earlier?
We could detect it now with our technology. Yeah. So if the other civilization has our technology, they can detect the pulling and pulling of Jupiter. How much does Jupiter pull the sun? About a solar radius, or maybe a little more. Maybe a solar diameter. So it moves the sun back and forth about the same size of the sun. So the center of the solar system is actually not inside the sun right now. It's a little bit to one side because of the pull of all the planets combined. I'm not sure how that translates in radial velocity, but it's within what we can measure now.
I thought it was a few meters per sec, about a meter per second, wasn't it?
That's right, the sun, that's your thing, not mine.
Any other questions? Well, not seeing any hands go up, let's thank Pedro one more time for...
This is a nice project because almost any night that you go randomly, there's so many exoplanet systems that you can actually go out one night and there'll be a transit that night. There's almost like 80% or 90% chance. So it's routine now. It's clear and I go observing and there'll be a transit.
One more question?
One more question for you, Doctor. I think this week the announcement came out that we measured some light reflecting off of a exoplanet.
Yes, invisible light. I just read it on Facebook of all places. Yeah, but I just read the notice that basically, I think the first planet that was actually discovered, what's it called, 51 Pegasi or something like that?
Yes, yes.
That's actually, they could actually cancel out the star, the light from the star and get the actual glint from the planet, invisible light. Before, I think there have been other planets discovered, but there have been planets really far away, so that's kind of cheating. I mean, you get the close ones, those are the good ones. She knows better, I think.
Now, I was going to say, is there a central database for this exoplanet data?
Yes, there is. I don't remember the name now. There are several places. One is the extra. Let me. Since I'm here on the internet, if you allow me a little bit of patience, I can look for it. Favorites, where is it?
Or you can email it to me.
If you can't find it immediately, you could always email it to Teresa. I think you have her email.
Yeah, it's called the Exoplanet Transit Database. ETD, Exoplanet Transit Database. That's a place that you can find, it's a place where all the amateur astronomers that observe transits of extrasolar planets gather their data. Okay? And it's a very nice place because it has transit predictions. You can give it your longitude, your latitude, and it will tell you this night you can see this transit from this time to this time, the altitude of the star will be this, at the beginning, at the end, etc., etc. So it's a very complete site. And there is another one which I'll have to look for it, so I'll owe you that one. But that one actually gathers all the data from Kepler, from all the ground-based observatories, the space-based observatories, and that's where the light curves that I just showed you will eventually end up in that database for other people to use later.
Okay.
So there are several. If you really want to know about exoplanets, there's also the extrasolar or exoplanet encyclopedia on the internet, and some of the data of the curves I actually got from there. The graphs that characterize the exoplanets are from the Exoplanet Encyclopedia. They gather all the information, and you can do correlation of variables and stuff.
Okay, thank you.
This may be an incredibly stupid question. Could I see that transit with my eye in your 14-inch telescope?
You would not notice it because the light of the star would diminish
Yeah.
by 3% at most. And it would take hours the effect of the atmospheric extinction as the star goes closer to the horizon is much larger than the 3% decrease in light.
Very good.
So that's why you need the comparison stars, because they sort of decrease at the same rate, and then you could notice it. So it's not noticeable in by eye, unfortunately. You actually have to measure the photons.
Very good, thank you.
Are you using a standard eyepiece camera for this? And how is that a relatively non-noisy for this?
The question was, are you using a standard
You know, like little eyepiece
Oh, he
cameras
was
or-
asking if you're using a standard eyepiece camera. What you might describe? I think you said it was an S-Pig camera that you're using.
Yes, it's the Santa Barbara Instruments Group CCD camera. The model is the STL1301-E, I think. That model is not made anymore, but they have similar models anyways.
And
He has like,
what kind of field does that give you? How
I was going to change it here. From the field of view, it's about 23 minutes of arc in the bright ascension, and whatever scale that to like 18 or something like that on the declination. So let's say 20 by 20, it's a good average. So it depends on the camera, but it's 20 arc minutes by 20 arc minutes. It's not very big, but it's also not very small.
Are there multiple pixels on each one of these spots?
Oh, he's asking, are there multiple pixels over each star? How many pixels do you tend to spread your star over? And maybe,
Oh, I defocus on purpose. So sometimes it's, I don't know, the radius is 15 pixels sometimes.
Okay.
So sometimes I defocus a lot. I never go below like 4 or 5 pixels. I have very bad seeing here too. So the stars jiggle a lot, so there is no way I can come close to the diffraction limit of the telescope, which is about an arc second. The best I get is 3 or 4. So I usually stay around 5 or 6 just to have a nice little Gaussian.
Yeah.
And if the star's too bright, then I go even bigger until I start seeing the secondary in the middle. It doesn't matter. As long as it's not on 1 pixel, it's okay.
okay, Pedro, thank you so much. We really appreciate this.
You're very welcome. You liked it?
Oh,
Yeah, yeah.
Excellent,
Yeah.
excellent. And consider yourself an honorary member of the Big Bear Valley Astronomical Society.
Yay! Thank you. Am I getting a t-shirt?
Yeah, just stop on by and pick it up.
Hey, good excuse to go there and have a vacation.
Yeah,
Hey,
you're
you're
welcome
welcome.
anytime, and we might be able to work out a tour of the, I hear there's a solar observatory out there somewhere as well.
Yeah, some people I know work there, don't they?
We're kind of limited to the sun for a lot of reasons. This isn't the McMath here, I'm afraid. I'm certainly working on Don to see if we could entice him to bring Celeste out here. So maybe we can get a run out here one of these days. with that.
Okay, fun.
Actually, Don was out here and I showed him where the visitor bench was going. I was afraid Celeste might not fit, but he grabbed a tape measure and started actually sounding excited. So I hate to steal observers away from the McMath, but I guess not that much.
We'll be at the McMath the second week of May, so I'll talk to Don and see how that's going. Maybe push him a little bit that way.
That would be very cool. Pedro, thank you again. And
Welcome, thank you.
okay, take care.
All right.
Bye-bye.